So with us, we have Michael Freund from Fraunhofer IIS, and he's part of the Data Spaces and IoT Solutions group, and also the part of the chair of Technical Information Systems at the FAU Erlangen-Nürnberg. And he's basically focusing on enabling read-write link data interfaces for IoT, and uses semantic web technologies for that, where Web of Things and Solid are involved. And this is also part of his PhD topics at the university. He also has a Solid pod. I'll share it in a bit. Michael, the floor is yours, and go ahead and take the screen.
Yes, thank you very much for the introduction. As Ege already said, my name is Michael Freund, and I work at Fraunhofer IIS. And today I want to talk about how we integrated the Web of Things with Solid. And I want to talk about the architecture that we used, the benefits that we think this architecture brings, and the real-world application that we have. In general, I will start with a background on the Web of Things and Solid, so that everybody is on the same page. Then I will talk about how we combined the Web of Things with Solid, how we generate a uniform API for Edge and Cloud, and about our real-world deployment, which is at Munich Airport. And finally, I will conclude. So the first thing I want to talk about is, what is the Web of Things? And I think the Web of Things is about describing any kind of API for different IoT devices using any protocol. And for that, we use a thing description as an abstraction. And a thing description is basically a semantic interface description, which is an RDF, and the file is serialized in JSON-LD. So I will basically show it with this image. So we have different IoT devices, which can be sensors or machines and so on. And they use different protocols to communicate, like HTTP, MQTT, and so on. And each device is described with a thing description. So like the semantic interface description. And everything that the device can do is grouped into interaction affordances. And these interaction affordances are the properties which are used to represent the internal state of a device, actions, which allow invocation of long-running tasks, and also events that are used for asynchronous event data pushes. And based on that abstraction, we can develop Web of Things applications. How does a thing description look like? So this is an example thing description of a sensor. And we have semantic annotations on top, for example, using the Zaref ontology, where we can define that this sensor is of type Zaref sensor. Then we have thing metadata, which means that we have a title for the sensor or a description what the sensor does for humans. Then we also have security data, which allows us to figure out how to interact with this device and to authenticate ourselves. And then we have the interactions affordances. As I already said, these are the properties, the actions, and the events. And if we look at this property, which is called sensitivity, which is of type number, and if I want to read that property, I use basically the href formula, which tells me how to dereference and interact with the device. And using the protocol-specific vocabulary, I also know that I need to send a GET request. So that's basically a short introduction to the Web of Things. And next, I want to talk about Solid. So Solid is basically a set of specifications that enables a secure, decentralized, and access-controlled web data storage. And this storage is based on open standards, such as the Linked Data Platform, HTTP, and RDF. And the fundamental architectural design principle of Solid is that we separate data, which is in the storage, from the applications that use that data, so from the apps. This looks something like this. So we can have a solid server, which has LDP containers, and these LDP containers can contain other containers, but they also can contain documents. And now, if I have an application, it basically reads the data from the solid server and then processes that information and writes the result back to the solid server. And with that, I will be always, or I'm responsible of my data. And that's basically a good thing. And another thing about Solid is that I can have access control lists. And with them, I can set what resources the user can access. So for example, one user or application might be able to access these LDP containers and this document, but he won't be able to access these documents and these LDP containers. Yeah, so now is the question, how do we combine the two things? So on the one hand, we have the Web of Things, and on the other hand, we have Solid. And our goal was to be able to use IoT data and store it for long term, and then perform continuous analysis and monitoring on that data that we gather. And we also wanted to have fine-grained access control, which would enable participation of internal and external stakeholders, while we still want to maintain privacy and security. The initial situation that we had was, so we had a lot of individual IoT devices and a composite system, which is basically a more complex IoT system, which consists of individual IoT devices. And these systems produce dynamic data at runtime, for example, sensor measurements or something like that. And they also have associated static data, for example, manuals in PDF format. But these IoT devices are limited in computational power, the memory they have, and also the power, since a lot of them run on batteries. And therefore, we needed, or we couldn't make the data available on the devices themselves. So this was basically our challenge that we faced. And therefore, we need to find how do we offload that data to other components of the systems. In our case, is Solid. And we need the storage component with fine-grained access control to manage data as multiple stakeholders are involved. And not every stakeholder has the same rights as other stakeholders. So we basically came up with an architecture like this, where we have things in the lowest layer. So things are basically IoT devices described by thing descriptions. And they were constrained in energy, computation, and storage. And all of the IoT devices that we have are described with a thing description. So at this level, we basically have a common and uniform interface for our to access the IoT devices. Next, we said, oh yeah, we need an orchestrator, which is basically the glue between the things and the solid server. And it's an edge device, and therefore we said it is constrained in storage, but not in computation and not in energy. And the orchestrator basically gets the data from the properties and so on from the things, maps that data to RDF, and then uploads that RDF data to the solid server. And in this scenario, our orchestrator is a client, and the solid server and the things are servers, which is quite nice to have this separation. The solid server is basically our cloud storage, which is unconstrained. And the server is then used to store the static and dynamic data of the devices in RDF format. And it also hosts a task queue, which is accessible by users via HTTP. This means that users and stakeholders on top are able to access data from Solid via uniform solid interface, which is basically an HTTP RDF-based read-write link data interface to a RESTful server. And so we can view data, and if we want to give tasks to our machines, we basically post a new task to the solid server, which is then fetched by the orchestrator and distributed to the things that execute that command. So with that architecture, we were able to include the users and send control commands to the things. But if we look at the goals that we had before, they were that we want to have long-term data storage. This is something that we have in a solid server. And fine-grained access control, which is also something that Solid provides to us. So we can check that. But what is missing is the continuous analysis and monitoring, because no user wants to do that, but we need applications for that. And therefore, our next question that we try to answer is, how do we effectively integrate applications into that architecture? And we basically came up, or we found out that we have two kinds of applications that we want to integrate with different requirements. On the one hand, we have latency sensitive applications. These are applications that implement feedback loops and need access to near real-time data and only to a small part of the most recent data. So they only need data from the last 5 seconds, for example. And these applications are then used to send control commands to different devices. And these devices typically access the data at the edge very close to the devices so that we have low latency. On the other hand, we have the data-intensive applications, which are used to support high-level business decisions and really high-level process orchestration. And these applications perform long-term data analysis or machine learning tasks and therefore need access to a significant amount of historical data. So they don't care if the data is 5 or 10 seconds old, as long as you have access to multiple years of data. And these data is typically stored in the cloud, and therefore these applications typically operate in the cloud. So then we said, yeah, so just put the latency sensitive applications near the edge, near our orchestrator, and the data intensive applications near the cloud at the solid server. And we wanted also to be able to access the cloud from the latency sensitive applications. And then we faced new challenges. Namely, in the old implementation, the edge orchestrator was only a client, and now we want to access data, so it also needs to be a server. And it's kind of hard if we want to access data in the cloud and the edge if we have different APIs at the edge. And therefore, we said it would be much easier to develop applications if we could have a uniform API at the edge and the cloud. So basically an edge to cloud continuum, an API continuum, basically. And what we came up with was that we split the edge orchestrator in 2 parts. One that is still called edge orchestrator, which is only used at startup and basically creates the API structure in the solid server and spawns our new entity, the mediators. And the mediators, so this is the new architecture that we had, basically perform the tasks of the old orchestrator, namely mapping different data encodings to RDF so that we have one data format across the edge and the cloud, and map different protocols to HTTP, since it's a lot easier to use HTTP than other communication protocols such as Bluetooth or MQTT. And the mediator should be implemented as a servient. And we said that we want each thing should have one mediator, which basically is the digital replica of the thing plus dynamic data. So this would be like the most recent sensor measurements and so on. And as you can see here in this architecture, we have a thing 1, which is connected via IP and HTTP and sends the data in JSON. And we have a mediator that maps that data from JSON to RDF, and the protocol mapping is necessary at this step. And it basically offers an API where the latency sensitive applications can access the data, and also is connected to the solid pod where the data can be stored for long term. The same thing for thing 2, but this time it is connected via Bluetooth and WoT and sends the data in binary. So mediator 2 basically performs mapping to HTTP and the binary data to RDF. And with that, we have a uniform API structure in the cloud and at the edge, which is easier to develop applications for. So now I want to talk how we can generate such a uniform API. As I already said, we need to create a uniform API structure. We need to map the data to RDF, and we need to map protocols to HTTP. I want to start with how we create the uniform API structure. So what we do is our edge orchestrator discovers all the things and creates, based on the thing hierarchy, an API. So our API in the cloud and at the edge is basically dictated by the hierarchy of the things that we use. And the thing hierarchy is derived from semantic annotations in thing descriptions. The algorithm that we use for that is basically this. So we first generate the tree structure by creating tree node instances for each device. Then we establish the tree's hierarchy by setting up parent-child relations between tree nodes, which is guided in our case by SOSA hosts, and SOSA is hosted by annotations. And third, we generate URIs for each tree node by traversing the tree and mirroring the position of each node inside the tree. I have an example for that. So imagine you have this structure. So you have one standalone thing called thing 5 and one composite thing like thing 1, which consists of thing 2 and thing 3, and thing 2 also consists of thing 4. So our API would, for thing 5, would basically be the base URI followed by thing 5, since this is a standalone device. But for thing 4, it would be the base URI followed by thing 1, followed by thing 2, and followed by thing 4. As you can see here, we have basically thing 1, thing 2, thing 4. And this will be the LDP container structure that is created inside the solid pod and also at the edge. I have a video about how it works. So we have an implementation of that, and it basically generates a URI with the base example.org, thing 1, and then we have property 1, action 1, and event 1. So thing 1 has basically these interaction affordances, and all the data that is gathered is stored in there. And the same for thing 1, thing 2, with property 2, action 2, and event 2, and so on. And with that, we are able to create the uniform API at the edge and the cloud, which only differs by the base IP address, basically. The next thing I want to talk about is how we map different protocols to HTTP. And for that, so why are we doing this? So not all applications can support all protocols. A good example is Bluetooth Low Energy, since we require additional hardware for Bluetooth Low Energy, and you always need to be close by so that you can connect. And this is somewhat inconvenient when you develop applications. And therefore, we perform a protocol mapping based on the Web of Things abstraction using existing protocol bindings. And for that, we use the WoT methods as an intermediary representation in our gateway. So for example, these are the binding templates for HTTP. And we can see that get is mapped to a read property, put to a write property, post to an invoke action, and get to a subscribe event. And if we have a look at Bluetooth, we can do the same basically. So we can map read property to Bluetooth got read, write property to Bluetooth got write without response, invoke action to write with response, and subscribe event to notify. And we basically already have, so we must connect the read property via get to read. And this looks like that. So we basically have IP HTTP get, which is mapped to read property, and read property is then mapped to read, which is Bluetooth got. And we do this for write property and invoke action and subscribe event. And with that, we are able to transform the Bluetooth data or MQTT data to HTTP, which again is easier to access and implement in applications. The last part I want to talk about is how we map different data encodings to a uniform data encoding, namely RDF. For that, we want to have mappings that should be adjustable at runtime at the mediator level. So we don't want to hard code them. And for this, we can describe the mappings using the RDF mapping language, short RML, which is basically the de facto standard when transforming non-RDF data to RDF. And RML is a declarative language, and it works like this. So you have, for example, XML, CSV, or JSON as input to an RML engine, and the mapping rule in RML where you define how your RDF graph should look like. And then the engine basically takes in the input and transforms the data to RDF following the specified graph structure. We use for the mapping execution a program called FlexRML, which is our own development. Since other existing RML processors are basically targeting only cloud environments and are therefore not suitable for constrained edged environments. And therefore we have developed FlexRML from ground up. Here you can see the difference this makes. So this is basically a benchmark of FlexRML. So this is the dataset size, so 10K, 100K, and 1 million. And these are the mapping rules that have been used. So this one is basically a simple mapping. The 5ref is a self-join, and 5join is basically a real join between two datasets. And the blue bars are FlexRML, and the red one are Morph KGC, and the yellow one are STM RDF ISA, which are basically state-of-the-art knowledge graph materializer, but they are applied in the cloud. And here on top, you can see the runtime, the elapsed time to map that data, and you can see that FlexRML is basically the fastest for small datasets and also requires the least amount of memory, which is relevant in constrained edge environments. So therefore, we use that. And with that, we are able to map the data that we get to RDF. And now we have everything that we need. So we have data in RDF, protocols mapped to HTTP, and we have a uniform API structure at the edge and in the cloud. And therefore, I want to talk about our real-world deployment of this architecture, which is at Munich Airport. And our goal there is to take pictures of luggage and extract features based on that. So as I already said, we have a prototype of that, which is installed at the check-in counter at Munich Airport. The check-in counter processes around 3,000 pieces of luggage each day and has only, I think, between 2 a.m. and 4 a.m. there is no luggage, but otherwise it's evenly distributed. For the devices, we have 3 RGBD. So these are RGB cameras with an integrated depth sensor. So for that we can derive the size of objects. And these cameras are the Intel RealSense D435i. And we also have a camera controller that controls the 3 cameras. As a trigger, we use a photoelectric sensor, which basically indicates if luggage is there, and we can trigger our 3 RGBD cameras. The cameras are basically, so we have one camera on top and one on the right side and one on the left side, so that we can get an image of each side of the luggage. On the edge, we have one HPC that hosts the orchestrator and 2 mediators. So for the camera controller one and one for the photoelectric sensor. And in the cloud, we use a community solid server for our data storage. So the architecture looks like this basically. So we have the 3 cameras, which have a camera controller. So this is our composite thing. And this camera controller has 1 mediator. And we have the photoelectric sensor, which also has 1 mediator. And both mediators push their data into the solid server and retain like 5 seconds of the last data at the edge, basically. Then we have 3 applications. One control loop, which reads the mediator of the photoelectric sensor and checks if the sensor was triggered. If the sensor was triggered, we wait 2 seconds because this is the time it takes the luggage to move from the photoelectric sensor to the camera setup. And then we send a command to mediator 1 that we want to take images. So this control loop basically is responsible to generate images. Then mediator 1 annotates these images and sends them to the solid pod or solid server where we store the data. And in the cloud, we have 2 applications. One is the size and color extraction, where we basically generate a 3D point cloud out of the 3 color images and 3 depth images. And we extract the size of the luggage and the color. And we use that, or we want to use that in order to optimize loading planes for aircraft, because it is more convenient to move the larger baggage back in the aircraft and the smaller one to the front, for example. And another app that we have is the baggage type classification, which also reads the image, so just the color image this time, of the solid server, and then classifies what type of luggage it is. So for example, is it a backpack or is it a normal suitcase? And with that, this information we want to use to analyze, for example, if backpacks take longer in our process than suitcases, or if there's some kind of luggage that is especially slow to handle, so that we can find process improvements. This is our setup. So here you can see the cameras. Here is one from one side. Here's the top camera, and here is the other side camera. And this computer here is the camera controller. And the luggage basically moves on this conveyor belt from the bottom of the image to the top. And the photoelectric sensor is in front of that image, so it can't be seen, but it's around here. And if it is triggered, it sends a Bluetooth command, a Bluetooth signal to the mediator. Then the control loop reads that and sends a command to the camera controller, which then triggers the image capturing process. And here behind this wall on the back is basically the check-in. So this is where you leave your luggage and it is transported into the baggage handling system. This is an image from the top camera. So if you look at it, you can see, and this is a test luggage. And a 3D point cloud of that image would look like this. So you can see that we have some missing information, which is basically the white part, since we only take pictures from the side and from the top. And sadly, this luggage was a little bit too close to the wall around here, and therefore this side is also missing. But it is still enough to extract the dimensions of the luggage. And the data that we store in our solid server looks like this. So we have the first part, which is the top part. This is generated by the mediator that controls the camera controller. So we have an image, which is, we have some provenance information. We know what format it is, when it was generated, and where to find it. And we know what camera took this image. This is quite handy if you need to find some errors or do some troubleshooting. And we also have like the baggage top, which is just annotated, and we know what is observed. And this part is added by the image processing agent, which extracts the size and the color. And it basically reads the blue data, fetches the image from the solid pot, and then we have the agent that processes or performs the image processing activity and uses image 1 for that, and it generates the results and writes that back into the solid server. So we have the baggage height, which is 0.1, for example, and the color, which is FF0000. And with that, we have all the data and metadata inside our solid server. Yes, I'm already at the conclusion now, and I want to look back at the initial goals that we had when we started this. So first of all, we wanted to have long-term IoT data storage, and we wanted to have continuous analysis and monitoring on that data. And secondly, we want to have fine-grained access control to enable participation by internal and external stakeholders, while still maintaining privacy and security. So by combining WoT and Solid, we can achieve this. So first, we use we can integrate various IoT devices using different data encodings and communication protocols by using the Web of Things, which is kind of nice. Then we want to store the data and the metadata that we have with fine-grained access control to involve stakeholders. We can do that with Solid. And we want to enable the development of applications, which should be easy. And our applications only require support for HTTP and RDF. And the data can be accessed in the cloud and the edge by only changing the base IP. This means that we have the same API structure at the cloud and the edge. And this is thanks to the uniform API. So we can say that we achieved our goals from the beginning. Yeah, and that's it. Here are my contact information. If you're interested to get in touch, you can write me an email. And otherwise, thank you very much for your attention. I hope you liked it. And now I'm open to answer questions and discuss with you. Thank you very much.